Okay, you are able to see the slides, all of them? Yes, can you all see? Are you able to see the slides? I hope you are able to see the slides, right? Shall we continue? Yes, I want the responses.
Yes, ma'am.
Okay.
Yes, ma'am.
So in the previous class, what we had taken? We had taken the photoresist, right? The light sources, and also we had taken the photolithography, how it is performing. So if you want, let me go for a quick recap, right? What we had taken in the previous class. So we had taken the photolithography process, how it will be performed, and later we had taken the photoresist and applications. In that one, we'll be having positive photoresist and negative photoresist. So this one we had already taken here. In that one, we had taken the type of components used for photoresist, positive and negative photoresist we had taken. And later we discussed about the profiles of lines from photolithography. So what happens when we use negative resist and positive photoresist. So we had taken that one. And how do you apply that one, right? How do you apply this positive photoresist? The mechanism used for that one we had taken. And one disadvantage is nothing but the edge beads, right? So the edge beads, the photoresist coating with edge beads is the problem in case of the photoresist, which we had already taken itself here. And later we have taken about the light sources, right? What are the different light sources? We have taken about the mercury vapor lamp, right? And later we have taken the deep UV light is another form of the light source for photolithography steps here. And X-rays can also be used, right? This one also we had discussed in the previous session here. And later we discussed about the development of the photoresist, how we will be able to development here. We'll be using that one by the negative resist, right? So in the using the negative resist method, same thing we'll be using for applying the photoresist also we have discussed here. And if you want to remove that one, right? If you want to remove the photoresist here, you can remove that one. That method used for removing is nothing but the discoming, right? So discoming can be used here where we can remove the photoresist, excessive photoresist that has been applied here. So where it will be involving the mild oxygen plasma treatment on the developed wafers itself here. And that can be used for bulk of the resist here. And post baking is also used here, right? Here descoming is used after the photoresist is developed, and post baking is used if you have any residual solvent present here. So for that one, post baking is being used here. And later we discussed about the ion implementation here. So in that one, where we can force the free atoms such as boron or phosphorus here with the charged particles into the substrate here. So where we can perform the imbalance between the protons and electrons resulting to the atomic structure here, which is nothing but the p-n junction here. So in this implementation process, we'll be using the sufficient kinetic energy for the implantation here. And one more thing, I think we don't require any temperature for this one, right? Yeah, we require the acceleration of the ions here, right? Which where we'll be having the sufficient amount of kinetic energy here, and we don't require any thermal. I think thermal, right? We don't require any temperature variation for this method here. That's what we discussed in the previous session itself here. How we'll be applying this one we had already taken here. So ion implantation will be created by the ion source here, where it will be forming the form of beams, and these beams will be controlled by the beam controller here. So where it will be producing the electron beams here. So the ions are extracted from the substrate here in the gaseous state, that is in the plasma, right? And the ion beam that is the ion beam will be once again controlled by the beam controller here. So where we will be able to adjust the size and direction of the beam itself here, and we can energize that beam by using the accelerator tube or accelerator itself here. And these ion beams will be focused onto the substrate here, which will be protected by a shield or mask, which has been usually made up of silicon dioxide here. So the highly energized ions, they will enter the substrate and collide with the electrons and nuclei of the substrate here. So where they will transfer all the energy to the substrate here and finally form the p-n junction diode. And later we discussed here, right, how this one will be created. But when you see the distribution of the ion implantation cell, you can see we'll be having this p-n junction, but it will not be uniform. That's a drawback here. And that's a drawback here. The distribution of the dopant will not be uniform here. So where it will, the concentration will be high in the middle, and when we go towards edges, it will be almost negligible here, right? And here we can see, right, the isolation energy, how much it will be there, that is electron volt. So this one you can see the values for each of the dopants. And later we discussed what we discussed here. That's what I told, right? Ion implantation does not require any high temperature for the process here, but it will be major advantage, right? Major advantage for this one is that the thermal stress or strain will be there, which will be introduced between the substrate and the shield here. But the disadvantage is what? The distribution, right? The distribution, it will be more in the middle, and it will, when you go at the edges here, it will be reducing here. The higher concentration will be implanted at the middle portion itself here, but as we move away from the surface, it will be deteriorating here. So that's what we discussed here. The distribution, right? The distribution of the dopant into the cis substrate, we can represent that one mathematically using this Gaussian distribution formula here. So there is Ruska, right? Ruska is the person who has given the concentration of the dopant that is been determined across the n of x here. So n of x is equal to what? Q by root 2 pi delta rp e to the power of minus of x minus rp whole square by 2 delta rp. So what is rp? Everything we had discussed in the previous class here. And later we discussed here at 30 kilo electron volts and 100 kilo electron volts, what will be the delta rp and what will be the rp value. So this one we had taken, which is required for the problem here. We discussed one problem here, right? We had taken the problem in the previous class, right? How to calculate this dopant concentration in silicon substrate here. So what is the value of Q, right? And the dopant concentration at depth of x equal to 0.15 microcentimeter, how much it is. And if you take this concentration at 0.1% of the maximum value, what is its value? Later we had solved this one, right, in the previous class, and we had obtained, right? We had obtained till here, right? Till here we had obtained, right? Question number 1. And when you take this question number 2 here, we will be taking at x equal to 0.15 micrometer here. So for that one, we are trying to use it in equation 1 here. So what is equation 1? You can see this is equation 1. This is equation 1 here. So I'm taking this equation 1 here, right? So this equation we'll try to apply. Right? So once you apply that one, what happens? We are replacing the value of x by 0.15 micrometer here. So N max will keep as it is, e to the power of x. So x value is how much here? 0.15 micrometer will keep as it is here, minus. So what is the other value here? The other value is nothing but, you can just remember that equation 1 here. So what was equation 1? X minus Rp, right? So Rp is given here, but Rp is not known to you, but we have to take it from the previous table. So if I see it here, right? So if I see it here, you can see, yeah, here it is, right? You can see it here, all of them. If you see this figure, right? We can have this Rp value, how much it is. If I take it for 100 kilo electron volt, the Rp value for boron is how much here? It is 307 in the form of nanometer. Nanometer it is. So same thing, we'll take it here. So we'll take the same thing here also. Just I can't see this one. Yeah. So here you can see, right? We're taking 0.307, right? And the other one, right? The other one is 2 into 0.069. So this one is what? Delta Rp. So if I see it here, right? The delta Rp is how much? Delta Rp is 69 nanometer here. So same thing is being taken here also. So delta Rp is nothing but 0.06 microcentimeter here. So that conversion is been done in the form of meters. We will be converting here. So substitute N max is calculated here, right? So the N max value is taken as 30 into 10 to the power of 18, right? Given the value for you, substitute, and you'll be getting this N, right, at x equal to 0.15 micrometer is equal to 2.27 10 to the power of 18 per cubic centimeter here, right? This is the question 2 here. Later we have taken for question 3. So where we have taken what? The value of x to be equal to what now? The value of x is equal to x naught here, right? So now the concentration of this value will become what? N of x naught here. So this n of x naught will be equal to what? It will be equal to 0.1%, right? It will be equal to 0.1% of the N max value. N max value is 30 into 10 to the power of 18. So 0.1% of that value is how much? 3 into 10 to the power of 16. So that value will be taken here, right? We'll be taking that value, substitute the same here. So once you substitute, what we'll get? N of x naught we are supposed to calculate here. So we'll get N max value. So N max value you are supposed to calculate for that one. So Q is how much? Q is calculated here as 5.2 10 to the power 14. Substitute that one, divided by 2 into pi into right, into what? Delta RP. Delta RP is known to you, right? Is this one, right? 69 10 to the power of minus 7 e to the power of minus x naught minus the value, right? X naught is taken as 0.1% here, so we'll keep that one as it is. So minus 307, right? Substitute other values. Then we'll be getting this value equal to how much? 3 into 10 to the power of 16 here, right? So this n of x naught is given is how much? 3 into x to the power of 16. So substitute that one. Now you calculate x naught here. So what will be the value of x naught here? The value of x naught will be equal to 0.5635 micrometer. Understood all of them? Yes, understood?
Yes, ma'am.
So this is about the problem here. Now let us go for the next heading. I think I had given one problem for you, right? Only one change what you had to do. Instead of taking 100 kilo electron volt, you have to take 30 kilo electron volt and apply the same method here, what I had discussed in this slide. Apply the same method and try to find the values here, right? So solve that one as an assignment question here. Now, for the next heading, that is the diffusion here. So today we'll discuss about the diffusion. Tomorrow we'll go for the oxidation method here, right? So in diffusion method, what happens? We'll be taking the general principle of the diffusion here, where it will be applied to both the microelectronic system here and and it will be also introduced for the control amount of the foreign materials like dopants itself here into the selected area of the substrate here. So the principle of diffusion, what we have taken for the microelectronics, will remain the same in case of the MEMS also. So same method here, where we'll be using the control amount of foreign materials here and try to induce into the substrate here. And this process is what? This process is a slow baking process here. And where we'll be using this process here, we'll be using in the thin film buildings itself here. So that will be in the microelectronics and microsystems here. And all this diffusion process, what happens? It will be taking in the high temperatures. So that one you have to remember here. So how does the doping of the silicon substrate will take place? You can see it in this figure. You'll be having high temperature dopant gas here, right? You'll be having the mask, right? And this is the way how the diffusion will be taking place. The dopants will be moving towards the silicon substrate here. So the amount of dopant, right, it will be in the gaseous form here. So they will try to diffuse into the crystalline vacancies of the silicon substrate here, right? So in this will be in the crystalline form, but this will be in the gaseous form here. So you can see it here in this figure here, right? This one is a little bit different from the previous method, that is ion implantation method here, because in ion implantation method, what happens? In ion implantation method, we used to we are not using any high temperature there, but here we'll be using a little bit high temperature here, so that the gaseous liquid can move towards the silicon substrate here. So it is nothing but heat conductions, right? The method used in doping the silicon by diffusion method is using the silicon substrate method here. Sorry, using the diffusion process, like heat conduction method will try to induce the dopant gases into the silicon substrate here. So that method will be using it here. Now let us go for a little bit mathematical analysis for this diffusion method here, how we'll be using it here. So if you use this diffusion method here in the heat, I told you, right, we'll be using in the diffusion method, we'll be using the same similar to that of the heat conduction method here. So the mathematical model for diffusion is taken from Fick's law here. I will be using Fick's law here, which is similar to that of the Fourier law for heat conduction methods here. So same law, we'll be using it here. So what happens when you use this Fick's law here, we'll be using this, it will give this dopant flux, right? Dopant flux in the substrate to move in the x direction. So in certain direction only we'll be able to move it here. So that one is given by the x direction. So in the x direction only the diffusion process will be taking place when you apply this Fick's law here. Right. So here we can express that one, right? So you can express this Fick's law here using the diffusion of these foreign elements, right, or the foreign atoms to the substrate here of microsystems as in given in figure here. So you can see F is equal to minus d into dou of n of x by dx here. So this is equation 2. So this is the Fick's law here, where it has been applied to the diffusion of the foreign atoms into the substrates of the microsystems itself. So what is F? F is nothing but the doping flux, right? That is the doping flux is nothing but what? It is the number of dopants that are being passing through the unit area of the substrate in unit time here. So which is given as the atoms per square centimeter seconds here. So this is the doping flux here. So how many number of dopants will be able to pass through this unit area of substrate, that is given by the value of n. And d is what? D is nothing but the diffusion coefficient or diffusivity. So that one is measured by square centimeter per second. And what is n value? N is nothing but the dopant concentration in the substrate per unit volume. How much dopants are being present in one unit volume. So that one is given by n here. So this is the fixed law. This is the fixed law here. And the distribution of the dopant in the substrate here at any given time, right? At any given time, right? So this one is fixed law for the diffusion of foreign atoms here. But when you take the distribution of the dopants in the substrate at any given time, then the diffusion process will be obtained using this equation here. So this one is the fixed diffusion equation, which will be taken at any time itself here, but in the direction of the x coordinate here. So tau n of x of x comma t by tau t is equal to d into tau square n of x comma t by tau x square here. So this equation will depend upon the initial and boundary conditions here, right? This will be depending upon the initial boundary conditions that will be considered here, right? So what are the initial and boundary conditions? Let us discuss here, right? So the equation will be having what? It will be having the initial and boundary conditions here. One set of the initial boundary conditions, what? The first one is n of x of x comma 0 is equal to 0. This means what? We'll be having no impurity in the substrate here. So whenever you start the diffusion process, we will not be having any impurity in the substrate here. And the second boundary condition is n of 0 comma t is equal to n of s. So where n of s is what? It is the concentration at the surface here, which is exposed to the gaseous dopant here, right? And if I take the second boundary condition is n of infinity comma t here, so which will be also be considered as ns here. So where the diffusion of foreign substance is localized here, and the concentration will be far away from the exposed surface is negligible. Just a second. Yeah, so sorry, I had to receive the call here. Okay, so here you can see it in this figure. We are having this two boundary conditions. For the first boundary condition is what? The initial condition. Initially will not be having any purity. And if I take the concentration here, right, at the surface, right, the concentration is taken assumed to be equal to ns here. And the concentration which is far away from the exposed surface, so that surface is negligible, which will be almost equal to the value of ns itself here, right? So this is really the concentration of ns here, right? And if I take the concentration, the diffusion of the foreign substances localized here, and the concentration will be far away from the exposed surface is negligible here. So these are the two boundary conditions that will be applied to the diffusion process itself here. And the solution of the equation with initial boundary conditions, right, it will be having a form here in the form of the complementary error function. So that complementary error function is given here, it is, right? So if I take n of x comma t, right, so what happens, you'll be getting ns into error function of x by 2 root dt. So where this error function of this is nothing but the complementary error function here, which will be equal to what? 1 minus error function of x, which will be equal to 1 by 2 root pi integral from 0 to x e to the power of minus y square d by itself here. So these solutions, right, if I take these solutions here, it will be similar. This equation solution will be almost the same to that of the ordinary diffusion process here. So here we'll be having this complementary function here, right? You can see this complementary function, that is error function itself here from this above integral function, right? You can see. So these values of the error function, they can be available in the mathematical table that I'll give you, right? That I'll take in the next slide. So you'll be having all these values, right? You'll be having all these values in the table itself here. So using the table, you can get these values itself here, right? So these numerical values for this error complementary function, they can be obtained from this above integral form here. So where these error functions will be available in the tables, you can just take that value for the corresponding value of x itself here. Now coming to this equation here, what is root of dt? Root of dt is nothing but the diffusion length here. So where d is can be calculated for boron, arsenic and phosphorus. So this will be varying itself here. And how do we calculate that one, right? How do we calculate this value of d here? The value of d can be calculated using this equation here. So where ln of root d is equal to a of t complement plus b. So where d is what? It is the diffusivity. The unit of diffusivity is given to you here. So this is the one, right? If I take a temperature T complement equal to 1000 per T, then the value of T is equal to what? It is the diffusion temperature in degree Kelvin here. Then for that temperature, right, for the temperature 1000 by T here, so where you can take T equal to diffusion temperature here, for that one, the value of A and B is given to you for boron, arsenic and phosphorus here. So these values you can take it for solving the problem itself here, right? Now let us go for the problem. Right, now let us go for this problem here, right? We'll take one problem. So all of you take this problem here. A silicon substrate is subjected to diffusion of boron dopant at 1000 degrees centigrade with a dose of how much? 10 to the power of 11 per square centimeter here. For that one, what you are supposed to find out? Find out the expression for estimating the concentration of the dopant in the substrate. Second, the concentration at 0.1 micrometer beneath the surface after 1 hour into the diffusion process here, and assume that it is initially free of the impurity. So solve this problem here. So take down this problem, all of them. Let us take this problem. So I think you can take this problem, all of them. Yeah, so you can take this problem here, right? This is the problem here. So let us solve this problem, right? So if you see here, we are supposed to calculate what? We are supposed to calculate, first one is the expression for estimating the concentration of the dopant in the substrate. How much concentration do you require? And the concentration at 0.1 micrometer beneath the surface after 1 hour from the diffusion process. What is the concentration, right? That one we are supposed to calculate here. So let us take here, right? So first what we had to do, we had to calculate the diffusivity of the boron here, right? So in order to calculate the diffusivity of the boron here, we require what equation? That is 8.6, because I not calculated here. So that one is what? That is the LAN equation, the last equation what we had taken, right? So I'll just show it here. This one. So this one is the equation, ln of root d a of t complement plus b. So here we are supposed to calculate the diffusivity. So let us calculate the diffusivity for that one here, right? So with a and b. So a and b, where we will take? We have to take it from this equations here, right? So which one you are taking here? You are taking the boron dopant here. So for boron dopant, the value of A is what? Minus 19.9820, and B is 13.1109 here. So we'll take these values, right? And take the temperature here, right? So what will happen? This is the temperature T complement. This is the value of A, right? And B value from the table we are taking here, right? Let us find out the square root of the diffusivity. So the square root of diffusivity of boron is equal to how much? Root of D is nothing but 0.07534 here, or the value of D is equal to this one, right? This is the value here, right? So now we have calculated the value here, right? So the range, if you see this figure, so this 3.2, that one you no need to consider this one. The value of D need not be considered, but it is represented in that equation, which is around 2.10 to the power minus 6. So it is within this range. That's what it specifies itself here, right? So after calculating that one, we'll try to substitute the initial conditions. What are the initial conditions here? N of x comma 0 is taken as 0 here, and n of 0 comma t is taken as nothing but ns, which will be equal to how much? It is given by 10 to the power 11. So calculate that one here. And n of infinite comma 0 is equal to considered as 0s here. So now we'll substitute that one, right, in the error function equation. 8.5 is nothing but the error function equation here. So what happens? This is the error function equation, right? N of x comma t is nothing but ns into error function of x by 2 root dt, right? So nx is nothing but how much? It is 10 to the power 11. So error function of x by 2 root dt is been substituted. And how much we'll get? We'll be getting 10 to the power of 11 error function of 398.21 x by root 2. Root t, right? This is the value itself here, right? So this is the value for by substituting the initial and boundary condition, the n of x of t here. Right? This is the value here. So where the value of x is how much here? It is in micrometer and t is in seconds itself. This is the solution here. So this is the equation 1, right? The expression for estimating the concentration. This is the concentration here, right? The concentration of the dopant in the substrate. This is the dopant value here. Now let us calculate that one at x equal to how much? 0.1 micrometer, right? And at t equal to what? 1 hour. So after 1 hour, you're supposed to calculate here. So you'll take that 1 hour is equal to 3600 seconds here. So then what happens? We have to substitute the equation now n of x comma t. So x is 0.1 micrometer and t is 1 hour here. Now let us substitute, right? 10 to the power of 11 into 1 minus error function, right? X value is how much here? 398. It will remain the same, but x value are supposed to substitute as 0.1 here, divided by 3600 here. So what I'll get? I'll get 10 to the power of 11, 1 minus error function of 0.6637 is the answer here. This is the value, right? Substitute, then I'll get 3.482 into the power of 10 per cubic centimeter is the answer here, right? So this is about the problem, how we can solve it using the diffusion method here. Understood all of them? Yes, understood? I want responses. Did you understood all of them? The concept of diffusion? Yes? I want the responses.
Yes, ma'am. Yes, ma'am.
Okay. What about others? Jeevan, Kavya, Kavyanjali, Kiran? I hope you understood this concept of diffusion. So oxidation I want to take today, but I want to do it that one in the next class itself. So I'll stop this recording now.